Okay, good afternoon, everyone. I'm very happy to be here and see many familiar faces. So I'll start with a brief introduction of myself. So I originally came from Greece, and I got my bachelor in Athens, Greece. Then I moved to Stanford in this area, where I got my master and PhD under the supervision of Professor Rajiv Mothfani. And since then, I moved in Finland. And I work right now I'm a researcher in basic research unit of Helsinki Institute for Information Technology. And okay, it might sound a bit weird going to Finland from Greece and California. My perspective changed in many different ways. So I found that it's possible to walk on frozen sea and skiing on flat, and I enjoy very much doing sauna and things like that. So I'd like also to give you some information about the place I am and what I'm doing and how the place looks like. So I'm in basic research unit, and so our unit comprises of 3 areas. So this is data analysis, neuroinformatics, things like ICA, etc., and context-aware computing, which has a lot to do with mobiles and making mobile phones more clever, etc. The directors of our group is Professor Esko Ukkonen and Professor Heikki Manila. We are about 50 researchers, and the working environment there is very good. We have good funding. We can work on problems we like. We can host visitors. We can travel. So it's a nice place. My duties there is to do research, supervise students, and teach courses. And in particular, I'm a member of the data analysis group. So the research agenda of our group is to do data analysis for areas that they have, mostly for areas in science, that they have data and they have need for 2 analytic tools to make sense out of the data and extract some knowledge. And in particular, we collaborate with people in biology, genetics, oncology, atmospheric sciences. So what we are trying to do is to go and talk to these people that have the data and discuss about problems, abstract the problems, and thinking of developing methods for that problems, and if possible, taking the results of our findings back in practice and apply it to these methods. Okay, so I'm proceeding with a talk. So the main part of my talk would be on clustering aggregation, which is some work I did last year with Heikki Manila and Panagiotis Tsaparas. And I will also try to get some time to describe some other of the projects I have been working, and I give some overview of them, very small summary of what I have been working, if I get time. And feel free to ask questions at any point to interrupt. Okay, so our work in clustering aggregation is motivated as follows. So clustering is one of the well-studied problems in data analysis and machine learning. And we have there are many different algorithms have been proposed with different characteristics. Our thesis, our motivation was that it might be able to combine many different algorithms and improve the clustering quality. So the idea is that if I have 10 favorite clustering algorithms, that all of them work okay, but some of them might make some small mistakes on some part of the data, then combining all of them together might improve the quality of clustering. So our task is that we start with some black box clusterings that have applied on some data set, and then we try to find a new clustering that disagrees as little as possible with the input clusterings. And as you can imagine, our work is motivated by, there's a lot of work in aggregating results in machine learning, for example. It has been a very useful paradigm. There are methods like boosting, bugging, etc. And also in web search. So one of the ideas, old ideas, has been that instead of trusting any single search engine, just perform my search in 5 of them and then try to aggregate the results and hopefully get a better quality of results. Okay, so I started with a small example here, very toy example, just to demonstrate the basic ideas. So I have, in that case, 6 objects, x1 up to xx, and I don't know anything about them, so they can be like points in some dimensional space or documents, images. So the only thing it has happened here is that I have 3 clusterings, C1, C2, C3, that I have run on these objects, and they have produced some clusterings. So the labels also here, 1, 2, 3, etc., are not so important. So the only thing I see is that, for example, the first clustering clusters the first 2 points together because it gives the same label. Okay, and the second, third, and fourth points together, fifth and sixth, and so on. And then the same for the other clusterings. So if I have a new clustering C, then I can count the disagreement with all of those input clusterings. For example, you see that on the first 2 points and on the first clustering, C1, my new clustering C agrees because both of these clusterings place the points on the same cluster. Okay? On the other hand, C disagrees with C2 on the first 2 points because C2 says split the 2 points, put them in different clusters, 1 and 2, while C placed them in the same. So this is the measure, the notion that we would like to minimize. So these are, I will be more precise and I will give more formal definition, but this is the measure. And so this is another clustering C prime that has smaller number of disagreements, and I only want to point out here that in that case C prime and C double prime are identical. So it's just relabeling of the cluster. So it's 1 to 2, 2 to 3, and 3 to 1, if you see. So the labels don't mean anything, just the decision of which points go together to which clusters. Okay? So one observation that we made with this framework of clustering aggregation is that one can cluster categorical data. So this is one way to cluster categorical data. It has been some research on that and proposed specialized algorithms. But for example, you can see that in that case, I have a database table. I have some attributes. And now the idea is that view each attribute as inducing a clustering on the data. For example, the third attribute, job title, induces a clustering. So I have all programmers together, all project manager, sales manager together, and so on. Okay? The same for all attributes. And you see some of the issues here. For example, the first attribute induces a clustering that all the points are more or less singletons because each person has, I can say, a unique name in that company, say. Okay? Also, the second attribute, it's numerical. So again, it would be all points be a singleton, but I can also have, I can apply a clustering on one-dimensional, cluster all of these points to some range. So I can say the young people, some ages, I don't know, 15 to 25, and then so on and so forth. So again, the idea is that each attribute, it uses one clustering, and then by aggregating these clusterings, gives me one way to do clustering of categorical data. Okay? One of the issues in clustering is that often it's difficult to decide the number of clusters. So for example, we have formulations like k-means, where the objective function is minimizing the sum of square of distances of each point to a representative. And of course, this objective function can be trivially minimized by taking k equal to n, so it can become 0. Or if k equal to 1, then it gets some very large value. So how I go to select k in between? So usually there is no like a straightforward way to do it. There are some ways. Usually k is considered to be a parameter. So one of the advantages of our method is that it doesn't require to specify k. So we just want to minimize the number of disagreements, and then k comes naturally. So there is no trivial minimizer, k equal to n or k equal to 1, for example.
All the possible values of k and make something out of them?
Yeah, so we have tried that actually. One way to select some natural way of the number of clusters is take one data set, try different k's, and then aggregate them. And then we have done some experiments showing that you get a good idea about k using this method. Of course, it doesn't work so well if you try very diverse values of k. If you try 1, 10, 10,000, 10 million, then it's going to get biased towards the larger values of k. But if you have a rough idea what is k, and then you try different clusterings around that k, then it tends to give a pretty good answer. Okay? So these are some of the benefits of this framework. So it improves robustness. We can use this framework for clustering categorical data. The framework does not need specifying a k. We can do outlier detection, which is a relating issue. So if we have many clusterings, and I have one point that all of these clusterings decide to place that point in a different cluster, then it turns out by our objective function that it is better to have that point as an outlier. Okay? And also some other benefits. We can discuss that more. Okay, so I'll start now becoming a little bit more formal about the definitions and what kind of algorithms we have proposed. So I have a data set, x1 up to xn, and then I have a clustering C, which is a disjoint partition of this data set, and a clustering is a function that gives a label to its data point, and this is the label of the clustering. And now the label is the same if and only if 2 points are on the same cluster. And now, based on this notation, I'm going to define the notion of disagreement distance. So for that, consider 2 points, u and v, in my data set, and 2 clustering, C1 and C2. So I first define what is disagreement distance on that particular pair of points, u and v. Okay? So I'm saying that the 2 clustering, C1 and C2, disagree, and the distance is 1, if they take different decisions about this pair. So one clustering decides to place them in the same cluster, and the other clustering decides to split. Okay? Oh, and it doesn't matter which clustering does what, if they disagree. Or if they both take the same decision, if they both place them in the same cluster, or if they both split the pair, then they don't disagree, so the distance is 0. And now I define disagreement distance between C1 and C2 to be sum of this distance on the pairs over all possible pairs on the data set. Okay? And you can see an example here. Again, I have a disagreement, for example, on the last pair of points, x5 and x6, because one cluster says they go together, the other splits them. So given these definitions, the problem statement is the following. We are given a data set, and we are given m input clusterings, which at this point, for this problem definition, we don't know how they came from. And the problem is to find a new clustering C that disagrees as little as possible with the input clusterings. Okay? And now we capture that by taking the sum of disagreements of that new clustering with each one of them. Okay? So this is the objective function. And we call this problem clustering aggregation. There is an alternative way to view that problem, and this is as follows. So consider the data set X, and consider, again, m clusterings. Now, I view the data as a graph, complete graph, and the edges have distances. And if I make the distances to be the fraction of the points, the fraction of the clusterings which the 2 points disagree, okay, then my clustering problem becomes finding a like a partition of this graph in such a way, the objective function is the following. For each point, so for each pair of points that I place in the same cluster, I pay for the distance between these 2 points, because these are the fraction of clusterings that disagree, and I decide them to put them together. So I disagree with all of those clusterings. While if I split an edge, I pay 1 minus that distance. Okay? So if I have some input clusterings and I make this graph, now this is, and I want to solve this partition problem, this becomes an equivalent problem. But of course, one might create such a graph without starting from input clusterings. Just have a graph and have some other way to get weights on the edges. Okay, so we call this problem correlation clustering, the problem on starting with a graph. And it's, as I just hinted, it's a generalization of the clustering aggregation problem, because you might create such a graph without starting from some input clusterings. And the reason that, in that framework we don't need to specify K is that we penalize for both edges inside the clusters and edges outside the clusters. Okay, so K comes, is optimized somehow without needing to specify what is a correct number of clusters. Okay, so here I have another example, but so this maps this instance of clustering aggregation to correlation clustering, and this is how I would form these partitions. And I want to cut only light edges and preserve these heavy edges. Okay, so these are the 2 problems we consider, and what we did about this problem. First, there is a very simple observation that for the clustering aggregation problem, I can obtain a factor 2 approximation algorithm. Okay, this is a very trivial way to obtain this algorithm. We also have an algorithm that works well. I mean, it gives approximation factor 3 for the correlation clustering problem, this more general problem that we also consider. And we also consider more practical algorithms, like agglomerative algorithm, etc. And we give also experimental evaluation of the framework of clustering aggregation. Okay, so there is related work on this topic. So people in machine learning and data mining have also considered other clustering ensemble scheme with different objective functions, like information theoretic ways and other ways, but not with this objective function. The notion of the problem of correlation clustering has been introduced by Bensal et al. For graph with edges +1 and -1. And okay, in our case, we consider the correlation clustering where the edges have special special values. So, for example, they were between 0 and 1. If you allow arbitrary weights, then it has been shown that the problem is equivalent to multi-weight cut, and thus it has a log n tight bound. Okay, and actually, as I said at the beginning, our work is from previous year, this problem I'm presenting, and meanwhile it has been improved by Aylon and et al. That have a very nice algorithm for both of these problems. So they improve both of the results. So for the clustering aggregation, they have an algorithm 11/7, and for the correlation clustering, an algorithm that gives approximation factor 2. Okay, so this algorithm works on expectation. Our algorithms works in the worst case, but still these are very nice. This is very nice work. Okay. So I'll start first by giving the very simple algorithm I mentioned at the beginning for clustering aggregation. So the observation here is that if I fix the points, the data points, and I view all possible clusterings on those data points, the disagreement distance is a metric distance on this space of all clusterings. Okay? And the reason is the following. So the disagreement distance composes of sum of distances, or disagreement distances on pairs. Okay? So before going to give you, to tell you that, by metric here, of course, I mean that this distance is symmetric, non-negative, and obeys the triangle inequality. So the reason that this is symmetric is that this sum of distances over the pairs, and if the sum of this d uv satisfies triangle inequality, then this the other d satisfies also the triangle inequality. And this is very easy to see why this is so, because this is the triangle inequality. So the only way that I don't get this inequality to be satisfied, because my distances are 0 and 1, is if the left-hand side is 1 and the other two are 0. Okay? But what does this mean? It means that if I have 2 points u and v and 3 clusterings c1, c2, c3, and the right-hand side is 0, it means that c1 and c2 agrees on the points, c2 and c3 agrees. So it has to be that c1 and c3 also agrees on the points. So this is the reason that that I get this property gets satisfied. And now I have a very simple and folklore argument for one median. So what I want to find is a clustering that it can be any clustering, right? But instead of considering any clustering, what if I consider one of the input clusterings? So I have a general metric space, and I want to find one median in that space. So if I take one of my input points, this gives me 2 approximation factor. Okay, so this is a very simple observation. And we have shown that for that case, so we call this algorithm best clustering. Just try all the input clusterings and take the one that minimizes the objective function. And we have shown that there are instances that this is tied, so that this situation, the solution can be 2 times far from the optimal. So this algorithm it has this nice guarantee, but we found that it's not very intuitive in many cases. For example, if you think of the case that we apply the algorithm on the on clustering the categorical data, then we don't find it very intuitive just to pick one of the attributes and cluster on that. So you'd expect that something, an algorithm would be able to do something smarter on this categorical data. So for getting something like that, we consider also, we work on the problem of correlation clustering, which is partitioning that graph. Okay, so what I would like to do here, so I remember I have this graph, and I want to find groups to partition the points in groups, so that I minimize the sum of distances within and 1 minus the distances for the points I split. Okay, so here to rescue comes again the triangle inequality that holds for, if we assume that it holds for the distances. Okay, so the idea is that if we consider some center point z and we take other points x and y that are close to z, then by triangle inequality, x and y have also to be close to each other. Okay? So the algorithm leverages this observation, and this is the following. So take the vertices in any order, any arbitrary order. So consider one vertex, u, then take a ball of all other vertices around that vertex u. So take all vertices that are in distance less than a half from that vertex u and make a ball. Okay? And Now look at the average distance of this ball with respect to that point U. If the average distance is smaller than some parameter alpha that we fix later, then, so all of these points are packed nicely within together, so we make that a cluster. Okay? Otherwise, if the average distance is greater than alpha, it means that that point is somehow far away from points within its ball. Okay, so we view that as outlier. So make that point a singleton cluster. Okay, so in either case, you have removed some points from your data set, either the point and its whole ball, or just the point itself. So take that points that you have already clustered, take them out, and repeat the process until you're left with no points. So we could show that if we choose alpha to be 1/4, then this algorithm is 3 times away from the optimal. Okay, and I'm not going to the details how this is proven. Okay, so this is our result. We also experimented with other algorithms that we found also intuitive and practical. So, for example, agglomerative algorithm, just standard bottom-up algorithm, merge close nearby clusters until the cost function does not improve. And also, we could show that in that case, if we start with m clusterings, then we get approximation factor of m minus 1, which is not very good, but for some small values of m is reasonable. And then in our implementation, we experimented with a local search idea. So assume that you have some clustering already, maybe obtained with one of the previous methods. Now start making local moves that might improve the cost. So take one point, U, and then see if you can improve the cost by putting it in some other cluster, or if by making it a singleton. Okay, and if the cost improves, that make this move. Otherwise, don't pick another point and continue until you make a fixed number of moves or until your cost does not improve. Okay, and we found that this also helps a lot. And also in practice, even though that alpha equal to 1/4 gives 3 approximation, we saw that it's better to consider larger values, like 0.4, for example. But again, this was empirical, and it might work for some data set, but not for some other. Okay, so one unfortunate thing about the algorithms is that they're not so scalable, so they are quadratic. So, for example, for correlation clustering, quadratic complexity is inherent because you start with this graph of all pairwise distances. So for the case that we start with the input clusterings and the quadratic complexity is not inherent, we consider how to make that more scalable. So our idea was to use some sampling. Okay, so just take a sample of the points, cluster them, and then for all of the other points, now you assign them to one of the clusters found in the sample. But in that way, if you have really small clusters that are far away, and your sample, and you don't sample from that clusters, all of the points would be said to be outliers. So you have a second step that we take all points considered as outliers, and we cluster them separately. So this was the idea of how to make this algorithm more scalable. For our experimental evaluation, I'll just give you some examples of results. So we did the results on synthetic data sets and real data sets. So for real data set, we mostly apply the framework to clustering categorical data, the way I explained it at the beginning. So to start with some very simple, like some toy example, just some illustration of how the algorithm works. So here is a really toy example that I created myself by clicking on some MATLAB screen, and then I applied default MATLAB functions to cluster the points. So and of course I tried to make this data set so that it has difficulties for all the algorithms. So for example, a human would cluster the rightmost clusters as separate, but I created a bridge in between so that I fool the single linkage algorithm, which makes a spanning tree and stops at some point. And I also had imbalanced clusterings, non-concave, something like one close to another, and things like that. Okay, so this is not a challenging, but it's just an illustration to show what is the idea. So if you apply to this dataset single linkage, then there is some mistake on the two rightmost clusters, and also these other two balls get together, and things like that. And then if you get another algorithm from MATLAB, like complete linkage, and you apply it to this dataset, again, you get some things that you consider mistake, like splitting the upper left cluster and splitting also this big cluster on the bottom left side and things like that. And average linkage, again, does a mistake. Wards clustering, some mistake. K-means some other mistake. So you can see now the lines of the Voronoi diagram on that large cluster on the bottom left side. And the idea is that if you aggregate all of them, you get some answer that what you would expect. Okay, but as I said, this is just for illustration purposes. For real data sets, we did experiments on data sets we downloaded from UC Irvine repository of machine learning. And so you use votes, mushrooms, and census data. One thing here that it's a bit debatable is how do we evaluate clustering? So what is the ground truth clustering? So what we did, it was that in all of this data set, you have one class that is usually used for learning, so for learning purpose. For example, in the vote data sets, you have members of US Congress that vote on 16 different issues, but you also have the information that if each person is Democrat or Republican. Okay? So what we say is that we don't use this information for the clustering, but we compare the clustering with that. So it's like using the clustering to do the classification test. So we measure, for each cluster we found, we measure the purity of the cluster, like how many of the what is the percentage of the majority class? This is the how much you classify correctly. So this is the purity, and the rest we call classification error, and this is how we measure the quality. Okay, so the first result on the votes data set. So I present different algorithms. So we compare again two algorithms, existing algorithms for doing specialized algorithms for doing categorical data clustering, so like ROC and Limbo. So my point, so what I want to mention here is that so our best algorithm, like local search, has a classification error of 12%, while both of the two other algorithms have 11%. But we had the advantage that K was discovered automatically from that data set, while for the other algorithms, they're not so parameter free. So you have to set K equal to 2 in both of them, and some parameters phi and theta that we asked from the authors of that paper, or we get from their papers what they would use. Okay, so this is the result on votes. And for example, on, yes?
Rock and limbo?
So the ROC is an algorithm, it's old algorithm by Sudipto Guha and Q Suksim and Rajiv Rastogi. And they use some notions of Jacquard coefficient to, so they say, so they somehow measure the distance between two values by common neighbors. So using the Jacquard coefficient, and they devise some metric like that. Limbo is by Andritsos and Tsaparas, who is also my co-author on this paper, and is, I think, information theoretic clustering on categorical data. So Limbo is doing really well. For example, you see in that data set, so this is the mushrooms. Okay, so we do like 10% classification error, or 11 for the agglomerative with 7 clusters, while Limbo does also 11 for 2 clusters. Yes?
Algorithm that you combine in your approach.
So, yeah, so in that case, we don't, so we use this idea to do clustering of categorical data. So we take its attribute, induce a clustering, and combine those. So just use the data. Yeah. And, okay, so in that case, we do better than ROC. We do worse than Limbo, but the idea is that it's not so specialized method and it's parameter free. Okay? And this is an example on how pure the clusters are found by agglomerative. So agglomerative algorithm finds 7 clusters. And here, okay, so the class here, so the 2 clusters that we consider real are classification on poisonous and edible. And most of the classes, 5 out of 7 of these clusters are pure. They contain only poisonous or edible mushrooms. Except, so the most classification error is caused by the first clustering. Okay, this is the most unpure cluster. Okay, so now another interesting point. For example, for census dataset. So this is some dataset on US population and attributes like income and marital status, education, things like that. So when we applied to that, our framework gives very many clusters, like 50 or 60. Okay, while actually the classes are only 2. Like in that case, the classes, they say if a person earns more than $50,000 or less. So it's not so fair to compare with other clusterings that, or we say that it's not very reasonable, meaningful anymore to consider the classification algorithm. So we get this somehow artifact that we get 50 or 60 clusters. But after inspecting closer the results, we find that many of these clusters are meaningful. For example, you have things like Eskimos, fishermen, and you know, very small data set that are, everything is different from the rest of the data set. So you have minorities of attributes that are there. Okay? So this is, again, okay, so I don't go to scalability because I would like to, okay, it scales okay, the algorithm, this is the point. So I would like also to get to some other projects that I have been working and give an overview. So in particular, so how much time I have? Because I started like 10 minutes after 1. Should I stop at 2 or should I continue until 10 minutes? Okay, thank you. Yes?
Earlier, you had a formula which expressed the distance that you use in the domain algorithm, where you consider both the sort of the distance between antenna for being a response. So you give them equal weight.
Yes.
So the question is, if you don't give them equal weight, does that affect the number of clusters that you end up with? Because it seems like giving them equal weight is also an arbitrary decision.
Yes, so can you repeat the question? Yes, so the question was that the objective function has it was somehow, so if you say that 2 points agree, if so 2 clusterings agree on 2 points if the 2 clusterings both split or both put them in the same cluster. So this is symmetric, while it is meaningful to also consider not symmetric, so to give different weights. So that's a very good point. So I think many of these algorithms can be adapted. In that cases, we didn't have a good idea of what might these weights come from. So we just stay on the higher level of the problem. But yes, I agree. In practice, you can play with these parameters. Okay. So I had prepared to talk about 3 projects. I think I will go only for the last one, so network immunization, because this is some work that I have been done recently, and I would like to continue on that general topic at least. And this is work I did with Georgia Koupis, Maria Terzi, and Panagiotis Tsaparas. So this is in the setting of complex networks, social networks, etc. So nowadays we have many data, man-made or systems, or that organized as networks. So for example, we have internet, computers to computer, web pages, point to other web pages. We have social networks. People have interaction with other people. Protein networks, like protein-to-protein reactions and stuff like that. And often, the operation of such a network is threatened by the propagation of a harmful entity throughout the network. For example, in social networks, in networks of people, in communities, we have diseases that get spread. In social networks, we have some gossip or panic behavior that gets spread. And so on. We have computer viruses on the internet. So the question is, how can we restrict the spread of the virus on the network? And this is a topic that has studied a lot in in our century because it's essential in epidemiology, and so there are mathematical models to study that problem and so on. So what we consider, and this is what, okay, I will try to point out where is our contribution and our work. But in general, the way we view the problem is that we have a network, G, so we view it as a graph with vertices and edges. And now on that network, we have a model that a virus propagates. So, and this model can be probabilistic or deterministic or something. And we also have an adversary. So this is somebody, some adversarial entity that places some virus on the network. So the adversary can be blind, like doesn't know anything, or it can be adaptive. So the adversary is aware of what is our strategy of restraining the spread of the network and try to place the virus in a place to do as much harm as possible. Okay, and our problem, our task is the following, is to devise an immunization algorithm that is given the network, is given some budget, which is a number of nodes, and it's aware, like we have a model of how the virus propagates on the network, And the task is to find k nodes on that network so that the spread is minimized. And you can think of some very reasonable immunization strategies. For example, if I pick the node with a max degree that might, and immunize that node, then I might avoid spread of the virus in the network. Okay, or picking a random might be a good strategy if I don't know anything about that network. So we consider study two cases of, so the algorithm, of course, the immunization strategies would depend on the virus propagation model, how the virus spreads. Okay, so we consider two cases. One is what is called independent cascade. So the idea is that we have a node, U, that at some point becomes infected at first time. And then at that point it becomes affected. It has some neighbors. So the node tries to infect the neighbors and succeeds with some probability P. Okay? So if the node U succeeds, then the neighbor becomes infected. If it doesn't succeed, if it fails, then it never tries again to infect it. So this guy, I cannot infect him, and I stop bothering. Okay, so this is the, so it's one-shot probabilistic model with infecting of one node to another. So for example, you can see that if I have P equal to 1, if I always infect all my neighbors, then in effect, if I place the virus in one place of the graph, then I infect the whole connected component that I start, if P equals 1. But in general, P is not equal to 1. So in that case, if I would like to immunize the network, I would select the node to immunize that minimizes, when I take out, minimizes the size of the connected component. Okay? So in the blind case, or when the adversary is blind, I would try. Thanks. I would try to minimize the expected size of the connected component. If the adversary was adaptive, I would try to minimize the size of the largest connected component. Okay? So for that, we propose a greedy algorithm that tries to minimize the expected size of the largest connected component. Okay, there are many details here. I'm not telling you how this is done. It's not so straightforward. But we found that this heuristic works better than immunizing the max degree node. So it always works better than immunizing the max degree node. Max degree, in many cases, is equally effective. So if the graph is random, okay, if the graph is random, everything works about the same. Even random strategies work the same. If the graph is power law, then max degree works equally well as this greedy heuristic. But if the graph is small world, in the sense that it has small average distance and large clustering coefficient, so this is what is called small world graphs, then this heuristic, this strategy is much better than selecting the max degree node. Okay, so this was one virus propagation model. Another one is a more dynamic case, where the virus is it's a birth-death process that evolves over time. And in that case, the model is the following. So if a node has the virus, then it infects a neighbor with probability beta. Okay, and I call that propagation probability. At the same point, also, if a node might heal itself with some other probability delta. So the ratio of the two probabilities, beta over delta, is what is called the infection rate of the virus in the network. And it is known from studies in epidemiology, mathematical models, that there is a threshold phenomenon, a transition phase in the graph. So I have this quantity 1 minus 1 over lambda 1, where lambda 1 is the maximum eigenvalue of the vector of the system. And if the infection rate is smaller than this threshold in the network, then the virus dies out exponentially fast. Okay, so our task, our immunization task, would be to select a node to immunize that minimizes the first eigenvalue of the system as much as possible. Okay, because this will bring the infection rate below to the to that threshold of the network. Okay. Thank you. Okay. So for that particular virus propagation model, the strategy we propose is the following. So you have the system matrix. You compute the eigenvector. Okay. Now each of the coordinates of the eigenvector corresponds to a node, and now you pick to immunize the coordinate that it has the maximum value in the eigenvector. And the idea for that is that since you want to minimize the eigenvalue, and the eigenvector is somehow is a vector, and the length of this vector corresponds to eigenvalue, and you want to minimize the eigenvalue, you better choose one coordinate that it's aligned the best with that eigenvector. Okay? So, and you iterate this process until the infection rate goes below the threshold of the network. And again, so we don't have a theoretical proof that this method is the one that brings the eigenvalue as much as possible. In fact, it is not. There are examples of networks in which this doesn't work. It's not the best node that brings the eigenvalue as low as possible. Okay, but what we found that this heuristic it works very well. So it works always as good as immunizing the max degree node, and for the same class of graphs, the small world graphs, it is much better than immunizing the max degree node. In many cases, max degree is very good, like scale-free graphs or other kind of graphs. Max degree is as much effective. Okay. And so this is an area I would also like to consider a study more, like social networks, information networks, how information spread on networks, and these kind of things. So summarize my talk. So I'm generally interested in problems in data mining, and I have studied problems in clustering, sequence analysis, 0-1 data, and social networks. And I would like to work in problems that have applications to real data. Okay, thank you.